In this video, we'll learn how to do regression analysis in Excel. Here is the problem and the data. So we have data on sales of sweatshirts in 48 US states. So the data is organized in columns here. The first column, column A, shows the state names. Sales is the sales of sweatshirts. Price is in dollars. So that's in Alabama, 200, let's say, sweatshirts sold when the price was $2.19. Now sales has I think this is in thousands, if I recall correctly, in thousands, but for the time being we'll leave it as it is, just for the sake of demonstration, because it doesn't matter whether this is in thousands or not. For regression analysis, what matters is that the figures are accurately measured. Yeah. Okay, so so the price is given per unit. Income is income per capita in thousands again. So for example, in Alabama, when the data was collected, the average income per capita was $13,000 a year. Now, temp column shows us the temperature, average temperature in Alabama. So this is for each of the 48 states listed here. Right. Now, we would like to estimate demand equation for this from this data. So how do we do this? Now, first of all, demand equation includes or let me write the demand equation. So that's probably a good start. Yeah, the best start would be to state the demand equation in simple forms. Quantity demanded is a function of, so it's a linear function of x1, x2, xn, right? So now quantity demanded is dependent, in other words, on various factors, including the own price of the product, price of substitutes, price of complements, income per capita or average income, and many other factors, weather, temperature. Yeah. So these x's, basically these unknown variables, are the factors. So they could be n factor. Right now we have, so let me put it in context. So sales of sweatshirts is a function of, or demand. So sales is measuring the demand, yeah, quantity demanded. So it is a factor of, or the function of own price, so that's price of sweatshirts per unit. Then income per capita. Temperature, average temperature. So this is basically the three factors that sales is dependent on. Temperatures are in Fahrenheit, I believe. Right, so we need to model the quantity demanded as a function of these. Since we're hypothesizing a linear equation here, the general form of this equation or function looks like this, something like this. So beta 0, so it's a constant, beta 0 plus beta 1 price, so that's plus beta 2 income plus beta 3 temperature. So this is the demand equation, multivariate demand equation we're going to estimate. To start with, we will estimate the simple linear regression, sales, function of price, own price, right? So that's what our first equation will be. Let's move on to the demand equation. Right, so let's insert, apologies, I'm not going to insert a pivot table, so I was going to go to a pivot table for some reason. So data, you go to data analysis, regression from the list, Okay, now let me go back to the equation we stated here. So this is the equation, yeah. So there's a random error term. I am skipping that. I'm just ignoring that for the time being, yeah, to simplify the analysis. So sales is given to us, price is given to us as variables, and then we have collected data there. We will be estimating this beta 0 and beta 1, and we will be focusing on the value of the beta 1 and its statistical significance, because it measures the partial effect of price on sales, or it tells us by how much sales changes when price changes by a certain amount of, let's say by $1. So yeah, so maybe we could say that when the price increases by $1, the sales changes by beta 1 units, right? So that's how it is. Now, in this form, I stated this as a positive sort of a coefficient estimate, but in theory and also in practice, we would expect a negative sign for this coefficient estimate. So this is our hypothesis, yeah? Because price and quantity of sales or quantity demanded are related negatively, right? When price increases, we would expect quantities demanded to go down, yeah? Okay, so that's what the hypothesis is. Or more broadly, if we go to the main equation, we would expect a negative value here. Income to have a positive value, because we would expect the sweatshirt to be a normal good. When income increases, we would expect this quantity demanded to go up. And temperature to be negative as well, because when the temperature rises, when it gets hot, we would expect the sales to go down, yeah, because people may not buy as many sweatshirts as when it's cold, right? So we would expect that to be negative as well. But we have imperfect data. We have very limited number of data points, 48 points, yeah, observations. So anything might happen. In other words, we might have we might get positive value for beta 3 or positive value for beta 1, because there are identification problems usually in demand estimation. Okay, so let's move on now. Input y-range, so that's our dependent variable. So as you can see, I clicked here and highlight all this, including the first row. Yeah, so the first row is temp row. I included that, and I'll tell you why I did that. So let's expand this and now highlight the input x range. So this is our range of x's. In this case, we have 1x for now. Yeah, so 1x. So that's the price of sweatshirts. That's done. So the data is fed into the function. Now, because we highlighted labels alongside the numbers, we have to make sure that we tick labels, right? So the headings are included there. Now, output range. We would like to have the output pasted right there. So I'm gonna say this is where I want the output to be. And we don't need the rest. We would usually diagnose the fit, but we don't need it for the time being. Okay, it seems I didn't highlight the equal number of data points. Let me have a look. So this is up to row 15. So why would I do that? Maybe I just exceeded the number of rows that needs to be there. So let me have a look. Yeah, that last line here. Also, last cell shouldn't be included because it's blank. So I'm gonna change that to 49 so that I have exactly the same rows and exactly all. I'll just highlight all the data that's available to me. Okay, so here's the result. This is the output of the regression that I just estimated. Right, so the numbers here are quite long, so we will need only 3 decimal places, yeah, to make the inference. What I'll do is I will highlight and only include the data that I need for the analysis. So copy that part. I'll be using one note to comment and annotate. Oh, this is small. Are we able to increase the font size? Let's see if I can. Yeah. That's enough, I guess. It's big enough. Right, so what is this now? So in this output, we will be analyzing the coefficients, the standard errors, R squared, and of course that as well, F stat, significance of F stat. So let's put this in context here. Let's put this in context. The context was, let's write down the equation, sales, beta 0 plus beta 1, price, yeah? Now, we estimated sales, and that is equal to beta 0, so that's beta 0 is this intercept, estimated intercept value, I mean, 49, plus, also, sorry, this is minus because demand equation has, we hypothesize negative value, so that's what it is here, yes, negative value, price. This is our equation, estimated equation with estimated values here and there. Now, what it tells here is this, if you interpret it and impose some economic meaning to it, is this. So if the price increases by $1, the quantity demanded, or in this case sales, decrease by 314.77 units. Yeah. So that's the $1 increase in price leading to or resulting in that much reduction. So 314.77 reduction in sales. So holding everything else constant or holding other factors constant. Yeah, we're not changing anything else. We're just changing price and trying to see what happens to sales. So that's what happens. And when the price is equal to 0, then this whole thing will be 0, right? So what's left is this. So that's the amount of sales. Yeah, this is the total sales when price is 0. But we will not be interpreting this in this context that way, because price equal to 0 means it's a giveaway, basically a product. So we're giving away the product for free. Okay, so all we need is this part here. Now, is this a statistically significant result? Well, we need to do this. We need to calculate the t-stat for that. T-stat. So the t-stat was beta hat over standard error of beta hat. Right. So that's my bracket. Now t-stat for beta 1 is then the beta 1 hat estimated value over standard error of beta hat, which is given here. So that's given there. That's the standard error. And this is equal to minus, so that's negative here, minus 7.97. Yeah, I'm using 2 decimal places. Right, that means this is highly, in fact, statistically significant. Yeah, highly statistically significant effect. So price has a statistically significant effect on sales. Now, usually our benchmark for deciding whether there is a statistically significant effect on between the two variables is when t stat is in absolute value greater than 2, roughly. In fact, it has to be greater than 96, yeah, 0.96. This is the benchmark value, but we just approximate it to the next round numbers, whole number, which is basically 2. So that's what we're looking at. And we have to say that this is basically in modulus, yeah? So modulus value of t-stat has to be greater than 2 or 1.96 in large samples. It's 2 basically, yeah? So modulus of 7.97 will be 7.97, which is greater than 2. So there's a statistically significant effect from price to sales. Now, usually the p-value would be less than 0.05 if t stat, yeah, this value is greater than 2 or greater than 1.96. So what we mean here is that we have a significant statistical significance at 5% significance level. Okay, moving on now. What else can we talk about here? Well, the next thing is R square. R square tells us that approximately 58% of variation in sales is explained by variation in price, right? Approximately 58% of variation in sales, changes in sales, is explained by the changes in price, changes in price, on price. Remaining 42% of variation is explained by some other factors that we did not include in this equation, right? So now we will add the other factors as our next step. Yeah? In the next round of analysis, we will add the other factors like income that we have and also temperature. You may add more factors basically, but we don't have data for them. So that's another practice material, practice for you, basically, practice idea for you. Now, FSTAT 63.6 tells us how significant the model is. The model is statistically significant because the significance of F, or the p-value in this case, of F in this case is like what, 10 zeros before 3 basically, yeah, before the decimal point. So that's going to be 0.00003 something 2155 or something like that, yeah. So this is basically highly statistically significant result, yeah. So it's we need to keep the model. We can estimate the model and make forecasts, but we will not be relying on single regression analysis, simple linear regression analysis. We will add more variables to the model and see what happens. So we'll run the multiple linear regression now in Excel. Okay, so let's move on to the next part. Again, we go to data analysis. Okay, now our y range stays the same as before, but we need to change the x range because we're going to include 3 variables now. So don't include sales because that's not part of the independent variables. X's on the right hand side of the equation, these are independent variables, and the dependent variable is y. That's usually on the left hand side of the equation or the model. So that's our output level, that's our output cell, and labels ticked done, and we have the correct range selected. Okay, now we got a new output that I'm going to copy. Here. Right, so let's see if I can get this magnified a bit. Right, again, we will now rewrite the equation. Excuse me. Sales now is equal to beta 0 plus beta 1 price plus beta 2, oh sorry, beta 2 income plus beta 3 temp. So this is our new equation, multivariate regression model. And in this context, if we plug in the numbers into betas, estimated values, I mean quantities, so that's the intercept value 514.26 plus beta 1 is now negative 242, so that's actually negative value, right? So we get rid of that, right? So this is a different value now. It was what? It was 314 in the original estimation. Recall that, yeah? Price. I'll put right price as P. I think that should save us some space. Plus 1.22 times, so this times the income, let's say inc, minus, or is it plus? Yes, and that is 2.9 temp, right? 2.93. Let's keep this as for consistency. So this is our model with estimated coefficients. This is also the estimated coefficient here, another one right here. Now, as you can see, it's a different value here now. Estimated coefficient is different because now we included more factors, two more factors, which generally we would expect to absorb their own effects. So as a result, we have a reduction in the coefficient estimate. So in the original estimation, our result was what? Minus 230 to 314, which means this was a kind of inflated value or overestimated value. So the as we add more factors, it becomes more accurate. The value becomes more accurate in simple language. So we are kind of removing the bias from this coefficient estimate, or the upward bias has been removed in this case. Yeah. So estimator was more like biased in the original regression. Now what this means is this. Now again, in this context, a dollar increase in price results in the quantities of demand or sales to decline by 242.97 units. Yeah, so holding everything else constant. So by increasing the price by that much, $1, let's say, we would see our we would actually this would result in a reduction in the quantity demanded by this much. So this is basically consistent with the law of demand. When the price increases, quantity demanded decreases. Now let's look at income. Income has a positive estimated value, which means as we expected, sweatshirts are normal goods. So when income increases by, let's say, 1 unit, in this case $1,000, let's say, the increase in quantity of sales will be 1.22. Yeah, so sales increase by 1.22. So that's a positive effect. How about temperature? Surprisingly, temperature has a positive effect here, which means basically if temperature increases by 1 Fahrenheit, we would expect the sales to increase by 2.93. This is counterintuitive, isn't it? As the temperature rises, people buy sweatshirts, which is not intuitive. Maybe there is a bias here. Maybe something that needs to be included in the equation is not there, but for the time being, given the data, we will make do with whatever we have here, with this given data. So for the purpose of demonstration, this is just enough. So I can also talk about bias, potential bias here as well. Now, are these estimated coefficients significant? Should we keep all these variables, in other words, in the model? Or do we have ones that are not significant and we can drop them from the model? So to do that, to answer that question, or the questions, we can look at the t-stats. Yeah. Earlier in my original estimation, I estimated the t-stats, but now I'm going to refer to this t-stats because they're already there, so I don't have to calculate them or show you how to calculate it. The t-stat for price coefficient estimate is minus 5.5. So if you compare this to value of 2, the modulus of this, yeah, basically remember the benchmark was if t-stat modulus is greater or equal to 2, then we have significant effect of the variable on the quantity demanded. So in this case, 5.5 is greater than 2. So there's a significant effect of price on sales, still significant. Now the t-stat for income, however, income coefficient estimate. However, is less than 2. So that's 0.80. This is less than 2, which means this is not this doesn't have a significant effect. So income changes do not have significant effect on quantity of sales. Yeah, demand, sort of on demand, I should say. Sales is not affected by income. Interesting. Well, the sweatshirts are not expensive. Usually, this may be the case that there is no significant effect on demand for sweatshirts. Now, moving on to temperature, notice that this effect is statistically significant. It's greater than 2, basically. 4.12 is greater than 2. That's a huge effect, basically. What I mean is there's a large t-stat. The effect is not bad, actually. It's 2.93. But what's not clear to me is why we got a positive value here. Positive 2.93. We would expect a negative value when the temperature rises, for example. We should expect the sales to go down. Yeah, because when it gets hotter, we shouldn't expect the sweatshirts to be popular. But when the opposite is also true, when temperature drops, we should expect sales to increase. Yeah, when temperature drops. But again, this is not happening, because when temperature rises, sales will rise. When temperature drops, sales will drop as well. That's strange, isn't it? Anyway, so that's the interpretation and the statistical significance analysis. How about the whole model? Is the whole model significant, or is it explaining large variation in sales jointly? Right, so are these three variables jointly explaining large variation in sales? So we'll have a look at it. Now this time adjusted R-squared, not R-squared, because R-squared is used only for when you have one independent variable like the sales on the y-axis, and on the right hand side of the equation you have price, just like this equation here, right? This equation. So here we can use R-squared as we did earlier. But with this multiple linear regression, when you have more than one variables on the independent variable side, on the right hand side of the equation, then you will have to use adjusted R-squared, because each time a new variable is added, R-squared will increase. So looking at R-squared will not be helpful this time, because well, we have a biased sort of value here. So adjust R-squared then adjusts basically that additional increase, such that we don't have inflated R-squared. Yeah. Now we look at this value here then as a result. So which tells us that roughly 0.68, so 68% of variation in sales is being explained by jointly this model. Yeah, these variables jointly by these variables, or the models. This whole model explains 68% of variation in sales. This is a large increase, isn't it, from the previous one? So we had 58. Yeah, so 10-point increase, 10 percentage point increase is really good. Yeah, it's a really good increase. So this model is also statistically significant. So we keep this model. We are able to make reliable forecasts if necessary. Yeah, when you make forecasts using price, income, and temperature values, it is possible to get more or less accurate result given the significance as well as the R-squared value of the R-squared. Now it's a cross-sectional data. It's more likely that we get lower than 90-70% usually. So this is normal in cross-section analysis. But when you do time series analysis, the R-squareds are usually inflated huge for many various reasons, of course, but we are not going to do that because we don't have data for that. Now, next thing is interesting one. Can we calculate elasticity of demand with respect to price given these results? Let's say for one state. Let's pick a number, but before that, let me put this down. So elasticity of demand with respect to price is change in algebra form, quantity over change in price, times price over quantity. Right, so what's needed here is this values for this. We need these values. Yeah, we need the values for this ratio. And given that we have P and Q, then we can estimate this ratio, value for this ratio, and usually that is this guy here, the coefficient of the price. Because notice this, if you remember, we interpreted this as the partial effect or marginal effect of price on sales, or in other words, when price changes by 1 unit, quantity changes by a certain amount. So that's this value here. Yeah, so that's this value that we're gonna plug into this equation. So equal minus 242.97 times now price over Q. Let's pick two numbers, two values, one for price and one for sales in this case. So let's take Arizona. So that's price 199 and 150 for sales. Price was 1.99 and this is 150. Yeah, quantity was 150. I'm sorry, I need to suppress that code for now. Right, so we need to estimate that now, or calculate, I mean. As 242.97 multiplied by 1.99 and divided by 150. 3.22, so that is minus 3.22. Right, that's interesting. In Arizona, in general, this is what the elasticity is for, with respect to price for this product. So 3.22, highly elastic demand, isn't it? If price increases by 1%, quantity demanded will decrease by 3.22%. This is an interesting result. But it is not a necessity for Arizonian or population in Arizona, people in Arizona essentially. Yeah, you could have a look at it from the perspective of Alaskans. Yeah, Alaska elasticity of demand with respect to price in Alaska, for example, it could be different, right? Because it's always cold there. It may be a necessity there. Oh, for the time being, I'm gonna, for the remaining 2-3 minutes, I'm gonna look at the income elasticity with respect to price. Income elasticity of demand, I mean, not with respect to price. So let's say, let me write this down. Income elasticity is basically change in quantity demanded over change in income times income over quantity. Now, again, this guy is right there, so I'll pick that, 1.22 times, so let's take Arizona again, income now this time, and we know the quantity, yes, so 150. We need income in Arizona, it's 17,000, so that's just enough to calculate this. 17 over 150, right. So 1.22 times 17 over the quantity 150, and that is 0.138, so that's 138. Inelastically demanded, basically with respect to income, it's an inelastically demanded product. Plus, this is a normal good because the income elasticity of demand is positive, yeah, in this case, 0.138. So when income increases by 1 unit, I should say income increases by 1%, the quantity demanded increased by 0.138% or 0.14%. So that's the interpretation here, holding everything else constant. Yeah, I forgot to mention that as well. So you need, this is important. We have to add that. Okay, so that's it, guys. In this video, we covered demand estimation and how we use the figures to estimate elasticities and also assess the significance of the model. Thank you very much.